The Bolzano Weierstrass theorem guarantees that any bounded sequence of real numbers always has a convergent subsequence. The question arises, is it true for a sequence of functions? Suppose you have a sequence of bounded functions, does it necessarily mean that there is a convergent subsequence? And what is the meaning of convergent here? Let's first clarify that. Definition. Let X be a metric space and Y a Banach space. Consider a sequence, or we say a sequence Fn from X to Y is pointwise bounded if we can find a function phi from X to R plus such that norm Fnx is less than or equal to phi of X for all X in X. We say Fn is uniformly bounded if there exists M in R plus such that norm Fn is less than M for all n in n. Okay, this first inequality is also for all n in n. So pointwise bounded just means that at every point the sequence Fnx you can find a bound for it. Uniformly bounded just means that the norm of Fn's itself are uniformly bounded by the single number capital M. Let's see a couple of examples to see what's going on. Example 1, consider the sequence x bar n, which are elements. I'm going to treat them as elements of C close 0 1 R. Okay, now we already know that close 0 1 x bar n converges to a function that is not continuous pointwise. Okay, so these are a sequence of functions that are uniformly bounded. Right, and they're uniformly bounded by just the number 1. Now because if you take a subsequence of x bar n, that will also have to converge to this same discontinuous function, it follows that no subsequence of x bar n can converge in the sup norm, right? Because convergence in the sup norm is same as uniform convergence, and uniform convergence would guarantee that the limit function is continuous. Since the limit function cannot possibly be continuous, the functions x bar n cannot converge uniformly. No subsequence can also have this property. So to concisely capture this, because compactness and sequential compactness are the same, we can conclude that C 0 1 R is not compact, right? So here is an example where if you have uniform boundedness, you don't get a convergent subsequence, and compactness also fails. Now a deeper question might be, okay, here we did have pointwise convergence at least. Is that at least guaranteed all the time? No. So that's example 2, which is a lot more involved. Let me just make a remark that later in this course you will study the Lebesgue dominated convergence theorem, after which this will be very, very easy to prove. But without some sort of convergence theorem from measure theory, you will have to appeal to some sort of clever argument. That's what we are going to do now. Consider the sequence sin nx defined on close 0 2 pi. Okay. What I'm going to do is the following. I'm going to produce for any given subsequence, I'm going to find a way to produce a further subsequence such that at some point it will not be pointwise convergent. So let me repeat that again. So given a subsequence sin nkx, I'm going to produce a further subsequence. So aim is to produce further subsequence that is not pointwise convergent. Okay, that is not pointwise convergent. Okay, so what we are going to do is the following. We are given this sin nkx. Note that this nks being natural numbers that increase as k increases, these nks sort of expand any given interval and makes it larger and larger. So what we are going to do is the following. Choose I1 subset of 0 to pi such that sin n1x maps I1 into half 1. Okay, choose some small subinterval of 0 to 2 pi such that sin n1x maps I1 into half 1. This is very easily doable. Please think about why this is possible. Now what we are going to do is choose n2 to be or rather choose k2 to be the smallest integer k2 greater than 1 such that sin nk2 of x maps surjectively to close minus 1 1. Okay, what we are doing is maps I1. I should mention that, otherwise it makes no sense. We have already chosen the small interval I1 such that sin n1x maps I1 to half 1. Now what we are doing is we are choosing k2 so large such that sin nk2x expands this small interval I1 to be a large enough interval that contains an interval of length 2 pi, so that sin nk2x will map I1 surjectively to minus 1 1. This is certainly possible. Okay, now what we do is choose the next integer, choose k3 such that we can find, or rather what you do is now choose I2 subset of I1 such that sin nk2 of x maps I2 into minus 1 half, minus 1 minus half. Okay, so this might seem a bit confusing what is happening. Let's draw a picture to make sure that we understand really what's going on. This is what we are doing. We have this 0 to 2 pi interval. Okay, what we are doing is we are first choosing a small subinterval I1 such that this I1 gets mapped to half 1. It gets mapped to half 1. Let me just make this bigger because I want to include the negative points also. So let me just make this a bit bigger. So somewhere here, half 1, zeros here. Okay. Now what you do is you choose k2 to be so large that sine nk2 of x again covers this whole minus 1, 1. It surjectively maps to minus 1, 1. Now choose a subset I2, a small subset I2, such that sine nk2 of I2 maps to this portion, minus 1, half, minus half, this portion. Okay. Now you can guess what's going to happen. We are going to consecutively choose smaller and smaller intervals and larger k's, so that this alternating between half 1 and minus 1 half keeps happening. So to be precise, what you do is having chosen km, find having chosen km and im, choose km plus 1 to be the least integer such that sine nkm plus 1x maps im surjectively to onto minus 1, 1. Okay. Just boost up the index so that im gets mapped surjectively onto minus 1, 1. Then if m is odd, choose I m plus 1 subset of im to be such that sine n k m plus 1 of x maps into minus 1 half. Otherwise, if m is even, choose im plus 1 such that sine nkm plus 1 x maps to half 1. Okay. Depending on whether it's odd or even, the index m, you just keep alternating between half 1 and minus 1 minus half. Now you'll understand in a moment why we are doing this complicated business. By the nested intervals theorem, this intersection of im is non-empty. Okay. Let y be a point in the intersection. Now it's obvious that sine nkm of x alternates between the values in minus 1 minus half and half 1. Okay. So this subsequence cannot converge. At y. So what we have shown is no matter what subsequence you choose, we can find a further subsequence that does not converge pointwise at this given point y. Note, these sequences sine nx are all uniformly bounded by 1. So uniform boundedness is not enough to guarantee that a sequence of functions will have a convergent subsequence. So we need something deeper than uniform boundedness, and what that is called is equicontinuity. To illustrate what equicontinuity is, suppose you have Fn in this BCXY, bounded and continuous functions from a metric space to a Banach space, and such that Fn converges to F in the soup norm. Suppose we are in this situation, this the most general situation that we are interested in. Fix x in x and epsilon greater than 0. Fix x in x and epsilon greater than 0. Okay. By continuity, we can find delta greater than 0 such that dxy is less than delta guarantees norm fx minus fy is less than epsilon. This is just the epsilon delta definition written out in all its glory. Now, since f minus fn norm is less than epsilon when n is suitably large, because we are taking fn converging to f in the soup norm, when n is suitably large, what this shows is we can use this epsilon by 3 trick that we have been using at least a half a dozen times in this course so far to show that norm fnx minus fny is also less than 3 epsilon for n large. Okay. So what we have essentially done is we have fixed a point x and an epsilon greater than 0. Using the fact that f is continuous, we have found a delta that works in the epsilon delta definition, and what we are saying is that this same delta works for fn's when n is suitably large. Okay, in some sense all these fn's are uniformly continuous, not just uniformly continuous, they're sort of continuous in a way that is independent of n. In other words, they are uniformly continuous, equicontinuous. That's the technical term, they're equicontinuous. Okay, now I'm going to leave a definition of equicontinuity and leave it to you to check that any finite collection of functions will automatically be equicontinuous in this definition, and therefore you can show that whenever you have fn's converging to f in the soup norm, they have to be equicontinuous. I'm going to leave that to you. Let's move on to the definition of equicontinuity. Definition. Again, the setup is x is a metric space. Let x be a metric space and y a Banach space. We say a family f subset of BCXY bounded and continuous functions is pointwise equicontinuous if for each x in x we can find and epsilon greater than 0. For each x in x and epsilon greater than 0, we can find delta greater than 0 such that if dxy is less than delta, then norm fx minus fy is less than epsilon for all functions coming from this family. So the choice of delta corresponding to epsilon is independent of the function coming from the set f. Then we say the set family f is pointwise equicontinuous. If you could choose this delta independent of the point also, then you say the entire family is equicontinuous without any further adjective. So the main theorem we are interested in is the Arzala-Ascoli theorem. There are many scenarios where this theorem is applicable, and there are many slightly varying versions of this. I'm going to present one version that's most suitable for applications. That's when the domain X is a compact metric space and Y is a Banach space. Okay. So in particular, when you have a compact metric space and a Banach space, these functions F will all be bounded at least by compactness. I hope you have solved that exercise that was given to you earlier. Okay, so without further ado, let me state and prove the Arzala-Ascoli theorem. There are several proofs as well. Most of them involve a diagonal argument. I am going to present an argument that does not involve any diagonalization procedure. Okay, so here is the statement of Arzala-Ascoli theorem. Arzala-Ascoli theorem. So let X be a compact metric space. Let X be a compact metric space and Y a Banach space. And Y a Banach space. A family F subset of BCXY is relatively compact. This B is sort of redundant in our case in any case, simply because we are starting from a compact space. So is relatively compact. Remember, this just means that the closure is compact if and only if it is pointwise equicontinuous, and each orbit, I'll get into a moment what this orbit business is. Each orbit fx, which is just defined to be what x maps to under the various elements of f, that's just f of x, such that f is in f. So you should visualize it as a set of points where this family f takes the given point 2. Okay, and each, let X be a compact metric space and Y be a Banach space. A family F subset of Bxy is relatively compact if and only if it is pointwise equicontinuous, and each orbit f of x is relatively compact in Y. Okay, so checking whether a family of functions that are continuous on a compact metric space mapping into a Banach space, you have to check equicontinuity and you have to check that each orbit is relatively compact. So let's go on to the proof. There is a slight trick in the proof. So proof. So necessity is left to the reader. Necessity is easy. In fact, we have already seen aspects of this necessity before we motivated the definition of equicontinuity. Now we are going to use one of the criteria for compactness that we have done, that is total boundedness. We are going to use total boundedness. We will first show, we will show that this script f is totally bounded. That will actually finish the whole thing by the general Hein-Borel theorem and the fact that BCXY is complete. Okay, now to show equiboundedness, total boundedness, we'll fix r greater than 0. Okay, now we have to show that a finite number of balls of radius r covers the set f. So our aim is to show a finite number of balls of radius r covers f. Okay, so what we do is the following. For each x in x, we can find a ball b of x such that if y is an element of b of x, then non fx minus fy is less than r for all f in f. Okay, this is just equicontinuity, pointwise equicontinuity. What I'm doing is, first we are going to use equicontinuity to choose a ball b of x for each point such that if y is there in this b of x, norm fx minus fy is less than r for all f in f. Remember, the goal is to cover the entire set f by finitely many balls in the space BCXY. Remember that. Okay. Now, by compactness, by compactness of X, finitely many balls, bx1 dot 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 bxn cover X. Okay. Now, we are going to focus on the orbits of these points x1 to xn, and we are going to exploit the fact that these orbits are all relatively compact to find out finitely many balls in the space BCXY that cover F. Okay. Now, each fx1, fx2 dot 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 fxn is relatively compact. That's the hypothesis. Relatively compact. Okay. Now, that means their union f of x1 union dot 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 f of xn is also relatively compact. A finite union of relatively compact sets is relatively compact. This is very easy to see. Okay. Now, we can cover, call this finite union capital F. We can cover F by finitely many balls, of radius r. Why is that? Because by the Hein-Borel theorem or whatever, this F is being compact. F being relatively compact, F closure is compact, and therefore you can cover by, there is no Hein-Borel theorem, sorry about that. Just the fact that F is relatively compact will mean F closure is compact. You can cover F closure by finitely many balls of radius r, therefore you can cover F as well. Okay. So we can cover F by finitely many balls of radius r. Let's call these balls by1 dot 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 bym. Okay. Note that these y1 to ym might have nothing to do with x1 to xm. Okay. Now, we are going to relate y1 to ym to x1 to xm. That's the key of the proof. What is the meaning of by1 to ym covers F? It just means that for each f in script F, the elements fx1, fx2, so let me just for consistency, let me just write this F in the same way so that I don't confuse you. So fx1, fx2 dot 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 fxn. Okay, this, you pick an element from script F. We know that the entire orbit, which we have called capital F, is covered by by1 to bym. That means each one of these elements, fx1, fx2, fxm, they will have to belong to one of these, each one of them, right? They may not all belong to the same for obvious reasons, but they will have to belong to one of them, right? And this is true for each f. Given any element small f from script F, if you consider fx1 to fxm, they have to be contained in one of these, but we don't know which of these they are contained in. Okay. Now what we do is, here is the part where we pull a clever trick. To make this precise that fx1, fx2, fxn is there in by1 to bym, what we can say is there is a map capital pi from 1 to dot 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 n to 1 to dot 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 m such that f of xi is an element of b of pi of I. Okay. Sorry, b of y subscript pi I. Think about this carefully for a second. This is just making precise the fact that fx1 will belong to one of by1, by2, bym. It could be 1, it could be more also. I'm not denying the possibility. All I'm saying is there is a map pi from 1 to n to 1 to m such that fxi will be in the ball y b of y subscript pi of I. Okay, so just pass this for a few minutes and you will definitely understand what is going on. Okay, now here is the key step. This pi map will change from function to function, right? Given any function, there will be a pi map is what we can conclude. There are only finitely many such maps, right? There are only finitely many maps from 1 to n to 1 to m. You can write down explicitly the number of maps also. There are only finitely many such maps pi. Okay, for each such map pi, let f subscript pi be the set of all f in f. Let me, for consistency, again write this f in this really ugly handwriting, such that f of xi is there in b of y pi I for all I equal to 1 to ... n. Okay, so that means I'm going the other way around. Given an f, there is a pi that does the job for us. I'm saying fix a pi and look at all those functions for which pi will do the job. Okay, and I'm putting that as f pi. Now obviously union of f pi's is equal to f. As you run through the maps pi, you look at all the possible maps from 1 to n to 1 to m and you take their unions. Obviously it will be equal to f. Okay. Now what we are going to show is that we will show that each f pi has diameter at most 4r. Okay, if you can do this, this will finish the proof. I will leave the rest of the details to you. It's rather easy. We will show that each such f pi has diameter at most 4r. So what must we do? Take f comma g coming from this f pi. You have fixed a pi. Take f comma g coming from this f pi. What we must do is we must show that norm f minus g is less than 4r, right? That will show that the diameter of f pi is less than 4r or less than or equal to 4r. Okay, now fix x in x also. What we are going to do is we are going to try to show that norm fx minus gx is less than 4r. That will finish the job for us. So assume for concreteness that x is in the very first ball bx1. Recall we had begun by choosing fixing an r and choosing n points x1 to xn such that bx1 union bx2 union ... bxn is a cover of x. Okay, now what I'm saying is, without loss of generality, we are going to assume, just for the sake of concreteness, that this given point x is in bx1. The argument will not depend on this particular index at all, and we are also going to assume that pi of 1 equal to 1. Again, it really doesn't matter. This is just for our convenience. Okay, then what does this mean? This just means fx1 comma gx1 are both there in by1. That's what this means, right? Now we just compute norm fx minus gx is less than or equal to norm fx minus fx1 plus norm fx1 minus gx1 plus norm gx1 minus gx. Okay, and this is certainly going to be less than 4r. This is certainly going to be less than 4r, and this finishes the proof. This finishes the proof that f is totally bounded. So this we can conclude that f is totally bounded. And from the results that we have seen on the section on compactness, it follows that f is relatively compact. F is relatively compact. So this concludes the proof of Arzala-Ascoli theorem. There is another proof of Arzala-Ascoli theorem that repeatedly you choose subsequences and do a diagonal argument. I'm going to leave that as an exercise to you. Okay, let me just end with one corollary of the Arzala-Ascoli theorem, which is the most useful version of Arzala-Ascoli in real life. Let X be compact and let F be the space CXR. Okay, I could choose BCXR, but it's the same because X is compact. Then F is relatively compact if and only if it is equicontinuous and bounded in the sup norm. Okay, note, not totally bounded, bounded. Okay, now proof. Necessity is straightforward from Arzala-Ascoli. I want you to check this. Necessity is straightforward from Arzala-Ascoli. Okay. Now, for sufficiency, we know that we have to show that f is equicontinuous, and we also have to show that each orbit is relatively compact. We are already given equicontinuity and boundedness in the sup norm. We have to show that each orbit is relatively compact. Now, each orbit fx is of course bounded. Each orbit is bounded simply because we are assuming that the family f itself is bounded in the sup norm. Okay, and therefore it is going to be relatively compact simply because we are in R. Therefore fx is relatively compact. Here is a crucial point where we require the fact that the codomain is R. It's not true in general that a relatively, a bounded set is going to be relatively compact. Now again Arzala-Ascoli finishes the proof. Arzala-Ascoli finishes the proof. So this version of Arzala-Ascoli is one of the most commonly used ones where the codomain is R. So this concludes this somewhat detailed and technical section. It's better that you actually go through the proof by yourself rather than hearing me do it. It's a somewhat involved proof. So please go through it carefully and work out the exercises also. This is a course on real analysis, and you have just watched the video on the Arzala-Ascoli theorem.